Hello there, our wonderful viewers on this favorite mathematics YouTube channel, Mathematics by Within Up. That special channel created for you and I to come together to tackle mathematics and demystify the age-long phobia often associated with this all-important subject. I wish to appreciate you sincerely for staying tuned and being our favorite and loyal subscribers. Thanks and God bless. Today, before we delve into the topic of discourse, I wish to recap from the last video whereby we looked at the topic differentiation, which I said is a popular word used for differential calculus. Calculus is a broad topic under which we have differential calculus and integral calculus. However, we are looking in depth at differentiation or differential calculus. And from our last video, we introduced the concept of differentiation, popularly called by students dy dx. And from there, I did say that different ways of asking individuals or candidates to differentiate are find dy dx, find the first differential coefficient, or find the first derivative of a function y with respect to a related variable. And from them, looked at some examples as intro. However, today we are taking it a notch higher. We are looking at something different entirely, and that is limits of a function. Limit basically is used from inception in deriving the differentiation formula, which we are going to go to in subsequent videos. That is a topic called first principles. Today, without wasting time, let's delve into the topic of the day. Evaluate each of the following. These are all limits. So when you see a limit question, the giveaway is simply the word lim, limit. So you are given, for example, question 1, evaluate the limit of 3x squared plus 8x minus 11 as x tends to 2. What you do essentially in limit is to substitute the values given. And it's as simple as that. So without wasting time, let's go straight into the solutions. For the very first one, we are to evaluate limit of 3x squared plus 8x minus 11 as x tends to 2. Now, for technical purposes, there is a difference between x tends to 2 and x equals to 2. As x tends to 2, it means x is approaching 2, not necessarily 2. Unlike x is explicitly equal to 0, 2 rather. However, that is technical jargon, you might say. But here, we simply insert 2 into the values of x, as though it were playing the role of equal to. We're going to see a clear-cut difference between tending to 2 and equals to 2 under continuity of the function in subsequent videos. Now, what do we do in this case? We simply replace the x with 2. Hence, we have 3 bracket 2 squared plus 8 bracket 2 minus 11. At this point, you don't need to put the whole of this limit again, just substitute. So 2 squared is 4 times 3, that's 12. 8 by 2, 16 minus 11. So 16 minus 11 is 5, and 5 plus 12 is 17. Hence, answer here is simply 17. And that's all. For number 2, on the other hand, we've got evaluate the limit of 16 minus x squared as x tends to minus 4. So all you need to do there is to substitute again. This time around, x tends to minus 4. So it simply means we are replacing the value of x with minus 4. So you have minus 4 all squared. Please don't make the mistake of saying minus times minus. No. Remember bracket first, bottommost. So you have to square this bracket before you work with the minus. That gives 16 minus 4 squared is going to be plus 16. And 16 minus 16 is 0. And that is that. It's as simple as that. I believe you find it quite interesting. Let's move on to solution C and subsequent ones. For C, we got 4x minus 4 over x plus 1 as x tends to 1 in this case. So the rule has not changed, except that we have a fraction here. So, however, there is a very important point I need to make here. Once you have a fraction, you have to be extraordinarily cautious. Before anything at all, you must mentally insert the value of x into the denominator. It's never allowed to have 0 as denominator. That would be called undefined fraction, which we have dealt with extensively in our previous videos, undefined fractions. You can have a 0 as numerator. That simply renders the entire fraction 0. But on no account must you have 0 as denominator. So if you're having a fraction question on limit, mentally try to substitute the value of x into the denominator to see if you're going to get 0. If you're going to get 0, then there's a different approach. So we're coming to that. But looking at this, if I substitute x as 1, I can't have 0, I'm going to have 2, so I can proceed. So no cause for alarm there. I'm just going to have 4 times 1 minus 4 over 1 plus 1. So that gives me 4 times 1 is 4. Then minus 4. 0 over 2 is still 0. That's perfect. You have 0 as a numerator, no cause for alarm, but not as denominator. Okay, there we are in question B. For question B, we got evaluate the limit of x squared minus 16 over x minus 4 as x tends to 4. Yes, here we go. As I mentioned in the previous solution here, if I mentally insert this 4 into this x here, automatically I'm going to have a minus 4, which makes the denominator 0. And that is red flag, it's not allowed. So what options are available to you? 2. Either the first thing you do is to try to manipulate or factorize, that's the appropriate word, the numerator, such that the denominator will cancel one of the factors. If that's not possible, then we're going to take a different approach entirely, and that's going to be L'Hopital's rule. So the first approach I believe is going to work because this is the difference of 2 squares. And that's going to become x plus 4, x minus 4. That's x squared minus 16 over x minus 4. So this x minus 4 will cancel out x minus 4. So the question actually becomes limit of x plus 4 as x tends to 4. We have not evaluated it. We simply just broke it down further. We simplified it. Hence, this is simply going to become 4 plus 4, which is 8. And that does it. Which I believe you're finding interesting. Okay. We've got 2 more to go. Let's look at question number E. E essentially is pretty much like the last 2 because it's also a fraction. And remember, when you have a fraction, you need to be extra cautious to ensure you don't have 0 as denominator. So let's see. I'm having x plus 2 as denominator here, and my x is tending to minus 2. If I insert minus 2 here, I'm going to definitely have 0 as denominator, which is not allowed. Okay. Then what is my first option? Can I possibly factorize the numerator such that a factor will cancel out this? No, it's actually not factorizable. Then we are open to the other approach, which is the L'Hopital's rule. What this rule is simply saying is very straightforward. When you are stuck in this case, all you need to do is to differentiate the individual components separately. Differentiate the numerator, differentiate the denominator, thereafter insert. So that's what L'Hopital's rule is saying. So differentiating this, we're going to have, and luckily, we have learned differentiation in our first video. So this is 4x minus 3. Then over this simply 1 as denominator. So I have differentiated. At this juncture, I can now insert my minus 2. So I'm going to have 4 into minus 2 squared minus 3. So minus 2 squared is 4. Times 4 is 16. And 16 minus 3 is simply 13. And that's it. It's that straightforward. Okay. I hope I'm not too fast. In any case, if you have any issue with any step, all you need to do, you've got the controls. Just pause, rewind, and do over and over till you get it. I promise you, it's quite simple. Then lastly, we've got this. What makes this last question different from all the previous ones is that x is not tending to a particular figure, rather it's tending to infinity. And infinity in mathematics means a very, very large number, really. So in this case, when you have this, you can't just insert infinity into it. No, that's not the way to go. Rather, once you see infinity, it's a completely different approach. Don't even bother trying to factorize. What you do is to follow this approach now. You divide each term by the highest degree of x. The highest degree is 2. This is x power 2. So I'm going to have 3, that's the numerator, x squared over x squared, plus 4x over x squared, minus 7 over x squared. That's the numerator. The same thing goes to the denominator. 5 x squared over x squared minus 9x over x squared plus 6 over x squared as well. That's step 1. Simplifying further, we're going to have this is actually 3 plus 4 over x minus 7 over x squared over 5 minus 9 over x plus 6 over x squared. It's at this juncture that I can then substitute the infinity. So that means we're going to have 3 plus 4 over infinity minus 7 over infinity squared over 5 minus 9 over infinity plus 6 over infinity squared. Now, here comes the trick. When you have a number, say, any number over 0, we say it's undefined, and that's the symbol for it, infinity. So vice versa, if you now have 5 over infinity as well, it's going to become 0. And in any case, infinity represents a very large number, extremely large number. So if you are now squaring an extremely large number, you are going to get an equal extremely large number, which is still infinity. Essentially, 4 over infinity is 0, minus 7 by infinity squared is still 0. Hence, this becomes 3 plus 0 minus 0 over 5 minus 0 plus 0. Hence, the final answer is going to be 3 over 5. And it's that simple. I believe you found today's class quite interesting and exciting and perhaps revealing. It's very simple. All you need to do, again, is to simply substitute the numbers given that x is tending to. And there's no cause for alarm once you're having just linear expressions. However, once you get to fraction, you need to take a break and look mentally at the denominator to ensure that by inserting the value, you don't get 0 as the denominator. If you have 0 as the numerator, you are good to go. There's no cause for alarm. But if you now have a value whereby you're going to have 0 as the denominator, you have 2 options open to you. The first option is to try to see if you can factorize the numerator so that you have some factors cancelling out. If not, then you're going to use the L'Hopital's rule. And the L'Hopital's rule simply means you are differentiating the numerator and denominator separately. After differentiation, you can then go ahead and insert the value of the x. And lastly, look at the case of the x tending to infinity. And that case is completely different, whereby we divide each time both numerator and denominator to the highest degree. By so doing, you'll be left with 2 whole numbers constants without any x. The others that have x will naturally vanish. So you are left with just the 3 over 5 in this case. And that's been the lesson for today. Thanks so much for staying tuned from the beginning to the very end. I appreciate you. Stay blessed and see you in the next class.